Okay, welcome to Conto. Today we try to this chapter 2, econometrics. So you cannot look back chapter 1, introduction for econometrics part 1. I recommend you to work and read once before continue from chapter 2. So in this chapter we try to look at a simple or linear regression models. Under this chapter I go with some overview of concepts of regression. Under 2.2 we have population regression function and sample regression function, assumptions of classical linear regression model. 2.4 is about estimating simple linear regression model. Then we try to do coefficient of determination, simple linear regression model. Then there is also hypothesis testing. Finally, we predict using this simple linear regression model. So, why we have care for regression? Because economic theory can give us direction of change. It means it is a qualitative information. But what if we want to know just how and how much? How can we model the relationship between variables? To do that, then we need a sample of data, a way or technique to estimate the relationship, which is used by regression analysis. So regression means nothing but estimation of econometric model. So in order to give answer for how one variable can relate it to another and about how much, we talk after we have get regression results. How means talking about a sign relationship, which is whether it's negative or whether it's positive. How much means in magnitude, based on coefficient or parameter we are talking about. So the concept of regression, historically, the origin was, the term regression was coined by Sir Francis Galton, which lived in 1822 to 1911, who studied the relationship between the height of children and the height of the parents. Galton found that although there was a tendency for tall parents to have tall children and for short parents to have short children, therefore the average height of children tended to converge or regress toward average height of the whole. The research was did by Sir Francis Galton, and which gives the origin of clue about regression for econometrics. So regress means go on average toward or backward a step. The modern definition of a regression go in other directions. In a sense, regression analysis refers to estimating functions which show the relationship between two or more variables and corresponding tests. It is a technique of studying statistical dependency of one left-hand side variables. What you call it is dependent variable on one or more right-hand side variables, which is independent variables, with a view to estimate or predict the average value of former, in our case, dependent variable average, on basis of fixed value of independent variables. So regression does not necessarily imply causation, because statistical relationship itself cannot establish causation or connection. Therefore, causation must come from outside statistics, ultimately from some theory or common sense. There are different terminology for variables of understanding. For dependent variable, we are giving a different name. Dependent variable or left-hand side variables have another name, like explained variable or predictant, or regression, or response, or endogenous variables. Similarly, for explanatory variables or for independent variables, which is from right-hand side variables, their name is explanatory variables, or independent variables, or predictors, or regressors, or control variables, or we call them exogenous. This is a different name or terminology for dependent variable and independent variables separately. You call dependent variable response variable or predictor variable, explanatory variables, regressors, or control variables. Therefore, regression analysis assumed that dependent variable or those named represented as stochastic. Stochastic means it is random, not fixed. It's random, which depend on independent variables. And independent variable is fixed or deterministic, which is non-stochastic. Non-stochastic means it cannot change, it's not random. Independent variable is not random. Sometimes it may be random, but as a whole it is fixed. So regression analysis assume as a way. Dependent variable is stochastic, independent variable fixed. So regression analysis has following objective and uses to show relationship among variables, to estimate average mean value or mean of the dependent variables given the value of independent variables, to test hypotheses about sign and the magnitude of relationship between variables, to forecast future value or values of a dependent variable by fixing independent variables. So it is to explain the variation in independent variable based on variation in one or more dependent variables. So when we say average or mean, average is when we have a small sample size. Mean means when we have large sample size, but in our case we look expected value, which is based on distribution function. So regression analysis indicates how variables are related, to what extent variables are associated with each other. Therefore, we have two types of relationship among variables: stochastic and non-stochastic relationship. We mean fixed and non-fixed, random and non-fixed. When we talk about non-stochastic relationship, for example, y is a function of x, is deterministic way or mathematical relationship, which is exact relationship. Okay, for individual x, the value of y is constant. So relationship between x and y is said to be non-stochastic if for each value of independent variable x, there is one and only one corresponding value of dependent variables. So if this domain and this range, for this all range, the domain is constant here in determining exact relationship. All observations fall on the line relationship on one line according to this relationship, which is not real in the world. The exact relationships are rarely encountered in business environments. If you have to look this relationship, which is stochastic, now we add new variables, which is random variables or irregular, which is called statistical or random relationship, which is inexact relationship. The relationship between x and y is said to be stochastic if for each value of x there are some values of y with some probability. Y cannot be entirely determined by x. Maybe there is another variable which is handled by u or return that they have determined y as well. So regression analysis is concerned with such relationship. They have the non-stochastic relationship if x has this value, exactly its y is this one. For x is this much, y is this much. So all observations lie on one line according to an stochastic relationship. But for dependent variable, for stochastic relationship, the observation may fall out of the line. If this is a line, fitted line, out of this line there is one observation, the other is above the line there is observation which cannot exactly fall on the line. So such like relationship is stochastic, not the exact relationship. It may be below line, above line. Okay, when we want to combine the observations, it may be for below the line, what? Or above the line. So we have a function like simple linear regression function, which shows that why it is simple. The term simple given for simple linear regression, which refers to the fact that we use only two variables, one independent and the other is one independent. We have only two variables. So it is simple, very simple. How we say it is a linear, which refers it is linear in parameters, and it may or may not be linear in variables. The parameters appear with the power of 1 and is not multiplied or divided by the other parameters in order to say it's a linear. So, simple linear regression is simplest form of regression analysis, having single explanatory variables which is related in linear form. That y is a function of f(x). yi, which is a dependent variable observation, I is observation, beta naught intercept plus beta 1 slope of xi plus ui is determinant term. Y is dependent variable, x is independent, beta naught and beta 1 are regression coefficient or parameters, ui is error term, I trick is case or observations. So the first term, the first two terms, beta naught plus beta 1 xi is determinist component, which is exact relationship between dependent and dependent variables. The second one is random or stochastic component, which is ui. So we have two components of simple regression functions. How you have now about u or error term? Error term is the difference from our observation, the difference between our observations and the fitted line. If this is line, y value is here. The difference from this observation to fitted line is error. Beta naught means intercept. Beta naught is positive. It starts from this point, then upward slope. When it is slope is beta 1. What does it mean? How we have get? First derivative of yi with respect to xi is equal to beta 1. This means if x is increased by 1 unit horizontally, y can increase by beta 1. Beta 1 increase in y due to 1 unit increase in x. So error term or determinant term is a proxy for all variables that are not included in the regression model, but may collectively affect our dependent variables. Why we include error term in the model? Source of error are, we have different source of error. Why we have included it? So the first one is why we include it captures effects of omitted variables. Why omitted variables matter? Lack of data and a limited knowledge. Okay, vagueness of theory, difficulty measuring some factors, heterodoxy of variables. Okay, principle or parsimony, keeping our model simple and manageable. The second one, the case is random behavior of human beings. Human reactions are unpredictable. Also, measurement errors matter. Why we include errors? Variables may be measured inaccurately. Wrong model specification, which can lead to wrong mathematical form or exclusion of important variables and inclusion of irrelevant ones. Aggregation error, errors in aggregation over time or over space. So error term is a term added to regression model to capture all variation y that can be explained by x's. The next topic is the population regression function and the sample regression function. When we talk about population regression function, the function that relates conditional mean of dependent variables with independent variables. It measures how mean value of y vary with x. If you look at the stochastic version of simple linear regression function yi as is found, when find it is expected value because it is about distribution, not the mean, not average. Expected value y given xi is equal to the function of xi, which is beta naught plus beta 1 xi. The expected value of ui or error term is 0 because error term may be positive, negative. When you have add on aggregation, the summation of positive and negative error term cancel each other and finally they become 0 on average. If you look at this line, this fit line, and this observed value, the function is from stochastic term, population regression function is this one. The difference between observation or yi to fitted line is random error. The expected value of this one will give beta naught plus beta 1 xi. For example, to find conditional expectations, if x is there, we have some group of people or their weekly income fall by this range 80, 100, 120 till 260 range. Their weekly family expenditure is 55, 63, 65, 70, 75 as well. Weekly family expenditure totally when the group of 80 weekly income fall 325 by adding 55 plus 60 plus 65 plus 70 plus 75, which is 325. On average, this conditional mean is when you have divided by 1, 2, 3, 4, 5 observation, and 325 divided by 5 is going to 65. When we are doing for a family which their weekly income is 100 and their weekly expenditure group is which go from 65 to 88, total expenditure is 462. When we have divided by 1, 2, 3, 4, 5, 6 observations, it's going to 77. For all the group, it could be going to 173 as well. Then there is sample regression function. Since sample is a counterpart of population, this is an estimation of population regression function on basis of sample information. So SRFs are approximation of true population regression function due to sampling fluctuation. From population, we have get this sample as yi high is equal to beta naught hat plus beta 1 hat xi plus ei. This is random error counterpart for it is sample. Since before we have ui, if it is population, now it's ei. Y hat for fitted line is equal to beta naught, estimator of beta naught, beta 1 hat, estimator of beta 1 xi is sample regression function. How we have get error term from these two equations? If we subtract this term, okay, if you have subtract this term from this term, we have exactly get ei, which is equal to yi minus y hat I. So where yi is estimator of expected value, so we have the error term as between. So we have three parts. Residuals, which is the difference between observed value y and the estimated regression. Error term is the difference between observed y and true regression equation. So error term is theoretical and never observed. It's also another explanation. We have go above parts, expected value of y given xi from population regression function we have get here. At this point, if this is the new sample regression function y I had, beta 1 hat plus beta 2 hat xi. We sample this population. Around the hat, this we have get from vertical line yi hat. Its whole observation is yi. So the difference between total observation to y predicted value and the sample regression function, the difference between total observation and the fit line is error or ui. Its sample is ei here. Now, note that on population regression function and the sample regression function, PRF is a realized concept which is unobservable, whereas sample regression function is observable. For a given population regression function, there are many sample regression functions. The primary objective for regression analysis is to estimate population regression function by using sample regression function. The disturbance term ui plays a critical role in estimating population regression function. For empirical purpose, it is the stochastic population regression function that's the matter. Assumptions of classical linear regression model, or the foundation of linear regression models assumptions. First, the basic framework of CLRM for regression analysis and based on set of assumptions, because statistical inference are valid if the model assumptions are reasonably satisfied in practice. First, the linearity assumptions. The model must be linear in parameters, but not necessarily in variables, since beta naught and beta 1 must be linear. X or independent values are fixed in repeating samples, means X is assumed to be non-stochastic or the same in all samples across samples. Variability in the values of dependent variables. X values in given sample must not be the same. Within a sample. The variance of X must be finite positive numbers. If Xi is equal to X bar or mean, it is impossible to estimate these parameters. Randomness of error term. The error term is assumed to be random variables. Zero mean for assumptions of the expected value of error term given independent variable xi must be 0 for all observation I. The error terms have zero conditional mean. This means on average, factors which are not included in the model do not systematically affect the mean of y. Positive and negative effect of ui tend to be cancelled each other. Therefore, parameter estimation requires known relationship between data and the regression function. So if we have x observations and y observations, if this line is population regression function, you have for xi, x1, error term may be negative if it is below line. If it's above line, it may be positive. When you have add positive and negative, they have the same range. When you have added together, they are going to 0. There is no any relationship between independent variables. Assumptions of homoscedasticity. Mean variance of ui. Error term given independent variable or xi must be constant. Constant or equal conditional variance of the error term. This means. So So the variance of error term is the same for all observations, which is the same across x values. Most of the time, this assumption is common in cross-sectional data. Questions. Who proves that the variance of xi given ui given xi is constant or sigma square? The homodystacity assumption is tell us, okay, the variance if this dot is for error term, the difference variation between this error term is constant. There is no any big difference between the points from origin to the last. This is homodystacity. Because yx here is similar amount of variance across range of values for x. But if the set like which is the gap, the difference between dot point for error term is going to large widely go from start to end or from end to start. There is difference, there is a variation which shows heteroscedasticity, which is when the variance for ui given xi is never constant in this diagram. About the assumptions of no autocorrelation or no serial correlations means the covariance of two error terms must be zero, where I and j are not equal. Error terms of different observations are independent. The error terms across observation are not correlated with each other. Also, the error term in one time period never affects the error time in the next period. This assumption is very common in time series data. Questions. Prove that covariance ui, uj must be zero. Also, try to distinguish between correlation and autocorrelation. If you have look A, we have horizontal line ui plus ui negative here. From right hand side we have positive, vertically positive. From right hand side we have negative. From below negative. If you have look at upward trend of this dot point for error term, this error term is going to in positive way. Positive way. If this line passes through the origin, it's going to in positive way. So there is positive correlation. Positive correlation. For B, this is downward slope, so it's negative correlation among the error terms. But if you have look at the diagram, there is no any sum relationship. It is simply in circulation, so there is no autocorrelation. Assumption 8. Assumptions of zero covariance between independent variable xi and the error term ui. This means covariance between xi and ui is zero. It shows no correlation between regressors and error terms, since xi and ui assume to have separate and additive effect on dependent variables. What if xi and ui are correlated? Prove that. Normality assumptions. Error term must be normally distributed on zero mean and a constant variance. UI is assumed to have normal distribution with zero mean and a constant variance. 10. No model specification error. The model is correctly specified. 11. Number of observations must be greater than number of explanatory variables. The assumptions of no perfect multicolority which come from chapter 3. Assumptions about the model, assumptions about error term, 4 to 9. Assumptions about data totally shows about no perfect multicolority assumptions. How realistic are all these assumptions? We must prove it. The base concept derived from above assumptions. Yi or dependent variable normally to fit while it have this mean with constant variance. Second is the such values of y are independent, mean covariance of yi, yj must be 0. Let we estimate simple linear regression models. It is about finding numerical value of population parameters when we say simple estimating SLRM. The parameters in LRM simple regression model can be estimated by different techniques of estimations. The most commonly used estimation techniques are Maidstone moment, which is old estimated, ordinal least square method, which we have used in this chapter, maximum likelihood methods. This method of movement is a method of providing numerical value of population parameters through replacing population assumptions by their sample counterpart. When we talk about realistic method, which is developed by Carl Gross, the most widely used estimation method, while it is a method which involves finding the values for estimates for which the sum of squared residual is minimized. It recalls for population regression function, which is shown by I is equal to beta or beta 1 xi plus ui. The simple regression function have these equations. Now, we need to find, according to OLS, the sum of squared residual must be minimized when we get residuals from sample regression equation function EI is equal to y hat observation minus y hat fitted line observations. Now, why I have this formula? The question is, how is sample regression function determined in such a way that it is as close as possible to population regression function? How to make sure beta naught and beta 1 are close to beta 1 or true population parameters, respectively? We call for minimization rules. The criteria is 1. Minimizing the summation of EI by choosing sample regression function in such a manner that the sum of residual is as small as possible. However, it is not a good criteria as it gives equal weight to all types of residuals. Okay? Because these all residuals have different area. The difference between these to the fixed line is somehow bigger than from this point to this line, or from U to the fitted line. The difference in vertical distance between observation and the fitted line observations is different among error terms. So as we have going to sum together, their summation may be in different amounts. So second, least square criteria, okay, which involves squaring the summation of error term. Error term means yi minus y hat I, then the summation from the rows, square the summations. So the sample regression function can be fixed in such a way that the residual sum of square is as small as possible. It is an important criteria. Why? 1. It gives fair weight to each type of residual. Second, its method is obtained by have some attractive statistical property. Hence, error term is go by this one, which after we have square and take sum both sides, we get this. We estimate beta hat, beta naught hat, and beta 1 hat in such a way that error term square is minimized. So we minimize error term subject to beta naught and beta 1 by using first order condition for minimization. Take partial derivatives with respect to beta naught and beta 1 at the minimum of error term square, then which is equal to 0 because it is first order condition criteria for both beta naught hat with beta 1 hat also. Then finally, the process of differentiation yields the following equation for estimation. Beta 1 hat is equal to n number of observations, summation of yi xi minus summation of xi times summation of yi divided by number of observations times summation of xi square minus in bracket summation of xi whole square, which is definitely represented as that way. The summation in bracket yi minus y mean in bracket xi minus x mean divided by the summation of xi minus x mean whole square. In division form, since yi minus y mean is y summation of yi is small, this xi is small, this one is xi is small. So in division form, we have summation of yi xi in over summation of xi square, while beta naught hat is equal to y mean minus beta 1 hat times x mean. If you need numerical properties of OLS estimator, reading the assignments, Gujarat, page 62 till 65. So there is some statistical property of OLS estimators and the Gas-Markov theorem. The first one, according to this theorem, which states, given assumption of classical linear regression model, that OLS estimators are below. Below means best, linear, and biased estimators. So it must be linear, means OLS estimators are linearly function of dependent variable y. They must be unbiased. Their expected value is equal to true population parameters. Expected value beta naught hat must be equal to population parameter beta naught. Also the same for beta 1. Best or efficient, which is OLS estimators have minimum variance among class of linear and biased estimators. So the summary of statistical property of OLS estimators, which is justified by Gas-Markov theorem, which states OLS estimator has least minimum variance, OLS estimator in class of linear and unbiased estimators. If you have time, you try to look this question, prove OLS estimators are below, otherwise you can carry it on in front. We have tried to prove this one next. Okay, we can start from proving the next day or next class, which can start from this one. Until this part, I hope that you have understand something about simple linear regression model for this chapter. Have a nice time.